Friday afternoon seminar. Welcome to this Friday afternoon seminar. So today we have Jacques Kluska as a speaker. So maybe there are quite a number of new people in the institutes, maybe a small introduction. So Jacques did his PhD at the University of Grenoble, which he obtained in 2014. And afterwards, he went to the University of Exeter to do a 3-year postdoc there. And after that postdoc, he came to Leuven. So he arrived here in 2017. He has been a postdoc at our institute since then. He's also the lead scientist of the Belgian VLTI Expertise Center, and he's specialized in circumbinary disks around post-AGB stars. And today he will talk about the possibility of second-generation planets. So please, Jacques, you have the floor.
Thanks, Joris. Hello, everyone. So, yeah, indeed, before coming to Leuven, I was mainly working on disk-round young stars, so protoplanetary disk-round young stars, to constrain a bit more planet formation. And I came here 4 years ago now to study this disk around post-AGB binaries. And I actually found that this disks are very similar to disk around young stars. And I think that's very interesting. And the question then arises that maybe these disks are also forming planets. And this is what I will be talking to you today. Of course, there are many people here. There's a whole group working on those post-AGB binaries. And you can see here a few names, and some of them are at our institute, like Ake, Hans, or Karan, for example. And there are also students that were at our institute before. Okay, so let's start the seminar now. Okay, so planets. So now we know more than 4,000 exoplanets, and most of them are formed around young stars. And we know that because around young stars, we see that there are disks of dust and gas that are called protoplanetary disks that are a byproduct of star formation, and we think that planets are formed within these disks. And so it's very interesting to study this disk observationally because it allows us to constrain the conditions, the initial conditions and the physical conditions of planet formation. But also we are looking for signs of ongoing planet formation to reconstrain the planet formation processes. And so with the recent instruments like ALMA, instruments of the Very Large Telescope, and the VLTI, for example, we can now image these disks. And what we see in these images is that there is a lot of substructures present in these disks. So there are like rings and gaps in this ALMA image, for example. From a sphere image, we can see that there are spiral structures and more chaotic structures surrounding the central star. There are some disks that have a huge cavity. So here is more than 100 astronomical units in a radius, a cavity in a disk. And so when the disk has such a cavity, it's called a transition disk. And there are also asymmetries down to very close to the central star at more or less 1 astronomical unit, where you see that the disk is not axisymmetric. And so the questions that we have is, what is the origin of this substructures? Are they due to disk-planet interaction, or are they leading to planet formation? So we would like to answer this question, and also we would like to know how fast do planets form, because there are more and more signs that planet formation is happening relatively quickly. All right, but today I will talk to you about second generation planet formation. And so what I mean by second generation is planet formation that happens around post main sequence stars. And so there are few candidates, planet to be candidates for such a second generation planet formation. And today I will talk about mainly about candidates around low and intermediate mass stars. So I will not talk about planets around pulsars, for example. And one such system is NN-SIR, which is eclipsing binary, a white dwarf M dwarf binary. And if you monitor this eclipses, the timing of the eclipses on the time, you see that the timing is changing with the orbital, I mean, at different periods. And so the change is very subtle. It's just only a few seconds. And there are several models to try to reproduce this timing variations. And one of the models is to put a planet or several planets around this binary system. And because of the gravitational pull that the planet will exert on the central binary, and because of the light travel time effect, we'll have this small shift in the eclipse timing variations. And so if you fit a model with 2 planets to this data up to 2011, you see that there's a prediction of a very strong signal that will happen in 2011. And this system was followed up, and the followed-up observations confirmed this prediction. So for this target, this model is quite reliable. And so this model consists in 2 giant planets, so 2 and 7 Jupiter masses orbiting at 3 and 5 astronomical units from the central binary. And the orbits are stable. And dynamical analysis have shown that they could not have survived the giant phase of the white dwarf, because the orbit will be way closer to the central binary and they would have become unstable. So there are very good candidates to be formed in such a 2nd generation protoplanetary disk. Even more, there was also a detection of dust by ALMA in this system that could be a leftover, a debris disk of the formation of these planets. But so these are the best candidates for 2nd generation planets, but they are also the best candidates for 2nd generation protoplanetary disks. And these are, I think, around post-AGB binaries, where you see very massive disks. And so, what is first the post-AGB phase? So if we look at single star evolution, so here you have the H diagram, you have the temperature here increasing to the left and luminosity on the y-axis. You see that the post-AGB phase is the most luminous phase of life of a low and intermediate mass star. And it's located between the giant branch phases and the planetary nebula and white dwarf phases. However, if there is a companion that is close enough to the evolved star, it will interact with it during the giant phase, because the radius of the evolved star will be larger, and you can have a very strong binary interaction. So you can have Roche-Loeb overflow. You can even maybe have a common envelope evolution. And so what we think is that this binary interaction will interrupt the single star evolutionary track and will eject the atmosphere of the giant, and will put the evolved star on the post-AGB track more early. And we also know that when there is such a binary system, we end up with a disk because we observe them around post-AGB binaries. Now we know that there's also some disks that are observed around some AGB stars that could be also due to the perturbation by a companion. But for the moment, I mean, it will be very exciting to know if these disks are really the post-AGB disks that are just forming, or if there are another type of object. So the evolutionary link is still missing, but it may be the 2 targets may be linked. And we know now in our galaxy 85 post-AGB binaries and 200 in LMC and SMC. So this target seems to be relatively common. And so now how do we know that when there is a binary, there is the formation of a disk? Well, if you look at all post-AGB stars, so the single stars and binary stars, and you look at the spectral energy distribution, you see that there is an infrared excess. So here you have the flux plotted against the wavelengths in micron. In black, solid black line, you have the fitted photosphere of the central star, of the post-AGB star. And we see that there is an infrared excess. So there is more flux in the infrared than just the emission from the photosphere. And there are two types of excesses. You have a shell excess that is more like a black body emission, and you have a disk excess where you need several black bodies to reproduce this, this kind of infrared excess. So we think that here this is the shell-like excess because you need just one black body, and usually it's the dust grains that are, it's thermal emission from dust grains, and they need to be at the same distance from the central star to emit just at one single temperature. So that's why we think that there's a spherical shell around this star. And here, when dust grains are in the disk, of course, they emit at different temperatures because they are at different distance from the central star. And so those targets were monitored with radial velocity to look for companions. And around shell-like stars, there is no companion found, whereas around disk stars, there is almost always a companion that is detected. So there's a very strong observational link between disk-like infrared excess and the presence of a companion. Another very interesting feature of those post-AGB binaries is the chemical depletion that is observed on the surface of the post-AGB star. So if you take a spectrum of a post-AGB, you can derive the abundance of different chemical elements on the surface of the star, and you can plot them on this kind of diagram, and you have the abundance of different elements against the condensation temperature. And what you can see is that for high condensation temperature, the element starts to be depleted, and they are more depleted where the condensation temperature is higher. And whereas the volatiles are not depleted at all. And so the interpretation of this is that the atmosphere that was ejected from the post-AGB that formed the disk are now, part of it actually is now reaccreted onto the central system. It's on the surface of the post-AGB star. And somehow the dust, so the refractory elements that are trapped in the dust are trapped in the disk or are not accreted again onto the central star. So for example, they can be just trapped here because there is dust sublimation radius. So when a dust grain arrives from the outer disk to the dust sublimation radius, it will feel a very strong radiation pressure and it will be blown away by the high luminosity of the central star, whereas the gas, the volatiles, will continue and be accreted onto the central star, for example. So I will come back to this depletion later on in the talk. I just want to emphasize that, for example, here, when you measure Fe over H for post-AGB binaries, it is not an indication of the metallicity, but it's really indicated how much of refractory elements, how strongly they are depleted in the post-AGB atmosphere. So the metallicity measurement is actually washed out by the reaccretion of this matter from the circumbinary disk. All right, and you see that this depletion pattern is seen in many objects and with varying strength, varying temperature at which the depletion starts. And so we need to find a way to try to explain this depletion patterns. And so the post-AGB binaries are studied mainly for stellar evolution because they are in consequence of binary evolution. They are just after a very strong episode of binary interaction. So if you know the products, we can constrain this binary interaction phase. There are some disbinary interaction going on. So I talked already about the accretion, but there is also exchange of angular momentum, for example. There are these interesting chemical properties on the surface of the post-AGB star. And there may be progenitors of these very nice protoplanetary nebulae, especially the bipolar ones. But today I will talk about these targets from the point of view of planet formation. So it's a different angle. So maybe I should have entitled my talk a bit differently. So I should have said like planet formation in post-AGB disks, Nobel Prize discovery, or fake news. So actually there's a lot of controversy about this idea. And I think that the truth is somewhere in between, hopefully. Of course, if you're watching that on YouTube, please let me know what you think in the comment section below. But well, we'll see in this talk how you can position in this debate. But more seriously, I think whether or not planet formation can happen in these disks, actually studying the physics and the physical conditions in this disk is very informative for planet formation processes that are happening around young stars. So here I'll give a few examples. For example, you can constrain the timescales of planet formation processes, such as grain growth, the formation of substructures, because around post-AGB, the post-AGB disks are believed to be very short-lived. So everything that we witness in this disk must have been formed in a very short timescale, so like a fraction of a million years. And there's also this, there's more and more hints in disk around young stars that planet formation happens actually very, very quickly, quicker that we think. For example, there's this mass problem where protoplanetary disks that are more, that have 1 million years or more are not massive enough to produce the observed exoplanetary systems. And so only the protoplanetary disks that are very young, so here class 0, class 1, so less than 1 million years, a fraction of a million years, are massive enough to produce the exoplanetary systems that are actually observed. There's also in young stars, so young stars are in star-forming regions, so their environment is quite crowded and they can interact with the environment. And it is, there are now evidence in few targets that there are some late inflows of matter from the original cloud, molecular cloud, that feed the protoplanetary disk and that make it, can make it unstable, favoring planet formation. Of course, in post-AGB systems, it's not the case. So the systems are isolated. So if we see some substructures, we cannot invoke the environment for them. And so we need to find another origin. Another example is planet-disk interaction. So when there is already a planet in the disk, actually it's more easy to form other planets because this planet will disturb the disk, will create some areas with high maximum pressure where dust grains can accumulate and form other planets. And here we can have the case that first generation planets so planets that were formed where the binary was young, could have survived the giant phase and then disturb the new second generation protoplanetary disk and further form planets. There are other examples, but I think that those already, I hope that I managed to convince you that it's interesting also from the planet formation community to study these disks. All right, so we want to study this disk observationally, and so we want to try to resolve these disks. And to know if you can resolve them, we need to talk about the angular scales that we need to reach to be able to see the details of these disks. So the binary is more or less separated. The binary separation, is about 1 astronomical unit. The inner disk rim is in dust, it's about 10 astronomical unit, and the outer disk rim still in dust is also about 100 or few hundred astronomical units. And so the typical distance to this post-AGB systems is 1 kiloparsec. So it means that 1 astronomical unit is 1 milliarc second. So we need very high angular resolution in order to see the details of these disks. And we cannot just use the 8-meter telescopes in the infrared to do so, but we need to use infrared interferometry to see the very inner regions here. So interferometry is a technique that combines different telescopes to synthesize like a larger telescope and to get very high angular resolution. And so we try to observe the targets at different wavelengths to really probe the different emission from this infrared excess, starting from the near infrared, where we observed the targets with the VLTI in Chile, with Pioneer and Gravity, and where we can resolve the inner disk rim, but also the separation of the inner binary. Then in the mid-infrared, we probe a slightly different wavelengths, and we also probe a different region of the disk, where we really can look for the inner disk structure. And then with ALMA, in the sub-millimeter and the millimeter, we can look for the cold outer region. So we can really cover the full disk structure and the full disk emission spectrum. And we can also add observations in scatter light with, for instance, a sphere on the Very Large Telescope that will look for polarized light, so photons that are scattered by the dust grains that are on the surface of the disk. You can also probe the surface of the disk actually in the outer regions with sphere. And so if we are able to combine all this observation, we can have a very nice ID and very good constraints on the properties of these disks. So today in this talk, I'll mainly focus on the infrared interferometric observations of this disk, but at the end of the talk, I will come back to the other observing technique and say some kind of observational perspectives on these targets. All right, so I will first focus on one target, RS-08-544-4431, that was already described by Ake a few weeks ago. And I will just describe what we know about this target. And then I'll go to the interferometric infrared surveys to know if other targets are looking like this target and if the larger population of post-AGB disks have the same properties. And then with this knowledge, high angular resolution observations, we can apply this knowledge to really study the spectral energy distribution and the infrared excesses to the whole sample of post-AGB disks that are known in the galaxy. And you have very nice results that I'm very excited to share later on. And then I will end up on some perspectives, observational perspectives on those targets. All right, so let's start with RS-08. So it's a post-AGB binary with an orbital period of 500 days and an eccentricity of 0.2. So you can see here the radial velocity data and the best fit model. And it has a very nice disk like SED where the infrared excess starts in the near infrared already. And so we observed this target quite heavily with the VLTI, with Pioneer, and we were able to make an image of the target. And so if we take the data and we reconstruct the image with just a monochromatic algorithm, this is what we get. So we just see mainly the central star. We see some emission from the surroundings, but the central star is contributing to from 50 to 60% of the emission. So we need to remove it from the image to see the rest of the target. And this is what we did using the Sparko technique. And here we see much more details of the target. So first thing that we see is that there is a point source. Oops, sorry. There is a point source here that is a bit shifted from the post-AGB star. And actually that is at the location of the secondary. It cannot be the secondary itself because it's a main sequence star actually. So the difference in luminosity is such that we should not be able to detect it. But what we think we see is this circumsecondary accretion disk. And actually this is in line with the fact that we see circumsecondary jets coming from the secondary actually. And we see them from spectroscopic time series. And so this was the PhD thesis of Dylan Bolen, where he studied for example, the H-alpha, the evolution of the H-alpha line profile with the orbital phase. You can see that here you have a nice double-peaked line profile, but when you go at another orbital phase, it transforms into the P Cygni profile and then come back to an emission, double line emission. And the interpretation of that is that we see a double peak line profile where we see mainly the post-AGB star, but then the secondary comes in front of the post-AGB star, or mainly the jet from the secondary comes in front of the post-AGB star, and it will scatter some H-alpha photons from it. And then this is how we see this P Cygni absorption. And then the orbital phase changes again, and we recover the original H-alpha emission. Of course, Dylan was very successful into reproducing this data with geometrical models, but now there's work done by Olivier Véran at our institute to reproduce this data with physical models of jets. that are actually jets that are models that are used to reproduce jets in Youngster objects in collaboration with Jonathan Ferreira from Grenoble. So it will be very exciting to get some physical properties of the targets from these models. So we see the point source, but we also see the ring, circumbinary ring here in this image, and the ring is at 1100 K, so it's very close to the dust sublimation temperature from silicates, for example. And if we remove the secondary, we see even better this circumbinary ring that has a radius of 8 astronomical units. And we see that it's not centrosymmetric. So it's really, there is some azimuthal perturbation. And so there is one maximum here in the north that we think is due to the fact that the post-AGB star that is very luminous is very close to this part of the disk. So it's an effect of illumination from the primary. But there is also secondary maximum here that may be due to this binary dynamical interactions. So like a spiral, for example, that is going through the disk. And so we started to make a model of this disk, an SPH model with a collaborator, Nicolas Coelho. And here you can see, so the binary, the disk, there is the dynamical truncation radius in gas, but of course we only see the dust. So we only are sensitive to the disk from this radius in orange here. And when you run the simulation, you actually see that it's very difficult to make an azimuthal perturbation, a spiral-like perturbation at this dust sublimation radius. So of course, it's still work in progress, but we need to know more to be able to say what is the final, the origin of this azimuthal perturbations that we see. Nevertheless, we try to model this target using a radiative transfer model that is used in the Youngster object community to model protoplanetary disks. And you applied it for this. This disk, and actually it was very successful because the model was able to reproduce the SED. So here you have the spectral energy distribution again. The model is in solid line. You have the photosphere here of the star, and this is the de-redundant photosphere. And it was also able to reproduce the visibilities from the Pioneer data very well. So you can see here that the data and the model are on the same plot. So they are really, so the model is really well reproducing the data. And the model has a relatively simple description. And so the main property is that it extends from the dust sublimation radius at 8 astronomical units out to 200 astronomical units. And it has a surface density that is increasing in the inner regions and then decreasing in the outer regions. And the total dust mass is about 2 × 10⁻³ solar masses. Of course, it's very difficult to constrain mass only from infrared interferometric observations, but we think that we are more or less in the right ballpark. But if this mass is true, it means that we have enough actually matter to form some planets if planet formation is actually happening. And we continue to monitor these targets with the VLTI, but at different wavelengths to really have a good constraint on the radial structure of the inner parts of the disk. So we did that in the near-infrared with Pioneer and gravity. So you can see here the squad visibility, that is the interferometric observable. And below you see the best fitting model that reproduces the data. So the model is in orange, the data is in blue. And here, this is the Matisse data in the mid-infrared, so at 3 and 10 microns. And you can see that in the near-infrared, there is the Gaussian ring at the single temperature that reproduces better the data. And in the mid-infrared, we have this disk with temperature gradient that reproduces better the data. So I wouldn't go into the detail of this work. This was done by Akke Corporal 3 weeks ago, but the interpretation of this of those results is that we do not have a geometrically thin disk, but we have a disk that has some vertical structure, so that puffed up inner rim, a curved inner rim that reproduces the best observations. Of course, now Akke is working on trying to use this radiative transfer model to reproduce all the data at once, all the interferometric data we have and the spectral energy distribution to really have very strong constraints on this on the disk structure. Okay, so now we know the disk structure around one target, but what we want to know is whether this target is representative of all other post-AGB binary disks. And this is why we led some interferential surveys in the infrared to probe other targets. And here I mainly talk about an infrared survey where we targeted 23 objects in the infrared, and we are again sensitive at the same structure as in the image that I showed you before. So the disk inner rim and the presence and the central stars. And we fit it to the data. So we have not done image reconstruction. So those are not image reconstruction. Those are the images of the geometrical models that were fitted to the data because we didn't have enough observations to make image reconstruction. But we fitted models with increasing complexity. And we then selected the best fitting model with the Bayesian information criteria that penalizes models with too many free parameters and that try to select the one that reproduces the data but does not overfit the data. And so the main conclusion of this work are that the disks, the inner disk rim, most of them are at the dust sublimation radius. So here you can see the size of the circumbinary near-infrared emission in astronomical units. And here in x-axis, you have the luminosity of the central star. And you have the sizes of the inner disk rims for post-AGB in purple here. And you have the sizes for the Jungster objects that are less luminous here in cyan. And you can see that this relation that we have, that the size is proportional to the square root of the luminosity, as what is expected when you have the disk inner rim, is still valid for post-AGB. So it's really extend for a large luminosity range. There is a small shift between post-AGBs and Jungster objects. And this could be due to the fact that the dust mineralogy is slightly different between Jungstars and post-AGB stars, or it can also be due to the fact that the gas density can be different at the dust sublimation rim. The second important result is that the radial profile of the disk are continuous. So how do we know that? We compared the size in the near-infrared with Pioneer at 1.6 micron with the sizes in the mid-infrared at 10 microns. And for simple models that have a temperature parallel with radius, you expect, so continuous disk models, we expect the objects to fall in this yellow area here. And this is the case for most of our targets. So they are compatible with a continuous radial profile. So of course, there are some outliers, but for most of the targets, this remains true. And the last important conclusion that we had is that the infrared emission morphology is very complex. So as I told you, we tried to fit different models with different number of parameters. And we then selected the models that fitted the best the data with a criterion that penalizes models with too many free parameters. And even with this penalty, we see that most of the data is better reproduced with very complex models with more than 10 parameters. So it means that we are we are sensitive to a geometrical model bias, and we need the image reconstruction technique to really recover the near-infrared morphology of those targets. And this is what we started to do with a VLTR large program to image 11 of those post-AGB disks with Pioneer and Gravity. And so this large program is called INSPIRING, that stands for Interferential Survey of Post-AGB Binaries with their ring. And so the main goal is to really recover the structure of the disk in a rim and see how it changes with a binary or orbital phase, and see if we detect the circumsecondary accretion disk in other targets as well. And the methodology that we use is that we start first image reconstruction to know what is the underlying morphology of the target. And then inspired by this image reconstruction, we built geometrical models to reproduce the data and have some values for the radii, for example, for the temperatures of the rings and so on. And then from these models, we go to a more complex radiative transfer modeling. And here are some preliminary images using an image reconstruction algorithm that we developed last year with Rick Kless here at the Institute, that is called Organic, that is using neural networks to make the image reconstruction. And we see that there are really different morphologies. So we have this that are inclined, for example. We have double rings around the star. We have a star with a companion. So you see a secondary here, or secondary accretion disk, but the disk is very, very complex, and there is a morphology that is very difficult to interpret. And we also see for RS-08, we had other epochs of the targets. And so we redetect the secondary at a different orbital phase. And we see that the azimuthal intensity profile of the ring is also changing with orbital phase. So that's very interesting. And we are trying to understand that evolution. All right, so now with this knowledge from infrared interferometric observations of these disks, we want to interpret the spectral energy distributions and, more importantly, the infrared excesses of all the targets of the post-AGB disks that we know of in our galaxy, to see what are their characteristics. And so if we look at the spectral energy distribution, so here again, you have the flux against the wavelength in micron, you see that there are already some differences that you can see with naked eye. So for example, here, so this is RS-08 still. So you see that the infrared excess starts in the near infrared, and it's a very nice full disk. But there's other target, like for example, AC-HER, where the infrared excess does not start in the near infrared, so not at 1 or 2 microns, but it starts further away at 3, 4, 5 microns. And then you have this disk-like infrared excess. And so we interpret that by the fact that there is no dust close to the dust sublimation radius. So there is something that is pushing the dust away from the dust sublimation radius. And so this morphology of the disk was confirmed by MIDI observations and radiative transfer modeling done by Hillen et al., where the radius of the inner rim of the disk is located at 34 astronomical units. That is 7 times larger than the dust sublimation radius. And so we wanted to know if these disks are actually common or not around post-AGB binaries, and if there are other kind of infrared excesses. And so to do that, we try to put the targets in a color diagram. And we use the near-infrared colors that will be very different for the two kind of objects, as you can see, and the mid-infrared colors, where here the infrared excess starts, and here the infrared color will be relatively different. And we put all the different disks on this color diagram. So you have the near-infrared color here on the y-axis and the mid-infrared color here on the x-axis. And you can see that the targets are not distributed randomly. So there's some structure in this diagram. And you can also see that the full disk of RS-08 is located here, where most of the targets, most of the disks are actually located. And the AC-HER object is located here at the bottom right corner of this plot. And so we wanted also to interpret this color diagram with some models. So we generated a population of radiative transfer models of full disks and of disks with a large cavity. So here, what is called in the Youngster object community, the transition disks. And we see that they do not overlap actually in this color diagram. So the full disks are located here, where most of the post-AGB disks are located as well. But the transition disks are all around. So they are in the bottom part of the plot, where there is a very low infrared excess, and also in the right-hand side of the plot, where the mid-infrared excess is very, very high. And in order to make sense of this color diagram, we just made some arbitrary cuts. We divided based on the location of the synthetic models. And we define some categories and try to put our post-AGB disks in the categories and see what are the group properties of each category and try to see if there are some interesting links that can out of it. And so you can see here that we define 5 categories. So category 0, 1, 2, 3, and 4. And so what we can do is first we can look at the infrared access for each, the disk in each category. So here, it's the median infrared access for all the disks. Okay, so we have the median here, and the gray area is between the 25th and the 75th percentile for the infrared access. And so this is really the median infrared access. And then we'll compare to this median the infrared access for each category. So for category 1, where there is most of the targets, of course, the infrared access follows this the median SCD of the post-AGB disks. And we think that here we have actually all the full disks are located here. For the category 0, we see that the infrared access is very, very strong. And this is probably because those disks are very inclined. So it means that the central stars are obscured by the disk. And so that the emission from the photosphere is very low. And we see a very high infrared access here. So here, we think that the disks are inclined. And we know that most of the targets, actually, there are observations that show that they are very inclined. Here we have, so the category 2 targets when there is no infrared access, but a very strong mid-infrared access. And those targets are the transition disks, so where there is no dust close to the sublimation radius, but there is an inner rim that is further away that takes all the photons from the post-AGB star, and that is very puffed up and emits a lot of, thermally re-emits all the emission from the dust grains that are heated there. Then we have the category 3, where we have low infrared access and the median mid-infrared access. And we think that here we have kind of a mix between full disk and transition disks. And then we have category 4, where the infrared access starts very, very late. So I think that here the inner disk rim is either very, very far, or the disk is relatively optically thin that we don't have a strong infrared access in the inner region. So it can be an analog of the debris disk that we see around young stars. So here, to summarize, there are all the infrared accesses from the different categories. And what we can say is that the color diagram actually is very good at trying to differentiate the different shapes of the infrared accesses for those disks. And so the first conclusion that we can say is that it seems that there is a population of transition disks. So around 10% of the targets have disks with very large cavities around post-AGB binaries. And that's very interesting because it's exactly the same proportion of transition disks that we find around young stars. So it may be due to the very similar physical processes ongoing. But there is more, and that's the exciting part, I think, is that there is a link between the transition disks, so the category of the targets, and the strong depletion of refractory elements. So here we come back to the Fe/H that is measured for those targets. And so it's not tracing the metallicity, but it's really tracing the depletion of refractory elements. And we see that for category 2 and some object of category 3, the depletion is larger than for category 1 and 0, for example, for the full disks. And so there is a strong link between the presence of a large cavity and the depletion of this refractory elements. And so it means that there is probably a mechanism that produces both this cavity and the fact that the dust is trapped somewhere in the disk. And I think that the most likely scenario is to put a giant planet in the disk that will trap the dust in the outer parts of the disk because of the maximum pressure that it will make on the inner part of the outer disk, but it will still let the gas through to be accreted onto the central star. So that's very exciting, sorry. I'm very excited. But yeah, we need to confirm the scenario. But if it's confirmed, it could be probably due to a first generation planet that survived the giant phase that is already massive enough to block the dust. But well, we'll explore all the different possibilities if we'll have more data. But I think it's very exciting to see this first signs of the presence of a planet within the disk. And such a link between the depletion of refractory materials and the transition disk is also seen in protoplanetary disks around Herbig stars, for example, but also around solar type stars, and more likely around many stars that have depletion of refractory elements. It is generally interpreted as the signpost of giant planet formation. All right, I will end up the talk now with some perspectives. And so first I will summarize the similarities and the differences between the post-AGB disk and the Young-Star object disks. So the similarities are that they have similar infrared excesses that we have seen. They are stable. I didn't have time to talk about that, but as seen in CO at large scale, we see a Keplerian rotation. The disk masses seems to be comparable with disks around young stars. There is evidence from dust growth with different observations. There's accretion and outflow, so we see jets, and also accretion from the disk onto a central binary. So there's angular momentum exchange. The inner disk rim is ruled by dust sublimation for full disks, as in young stars. And the overall disk structure can be reproduced very well with models, relative transfer models of protoplanetary disks. And we now know that there is a population of transition disks around those post-AGB stars. And there are also very interesting differences. So for example, the post-AGB star is very luminous. So it will push out the inner disk rim further away, but it will also exert a very strong radiation pressure. Thus, there are actually two students, so Silke and Anirudh, that are trying to quantify the effect of the radiation pressure on the dust grains in those targets. There's also a systematic inner binary in these targets because of the formation process that is very different. This is from this post-AGB compared to the YSOs. And there is no influence from the environment, so we cannot invoke that. And then maybe the presence of first generation planets that can perturb the disk. So maybe this is what we are witnessing here. And the short disk lifetime is very interesting to constrain the planet formation processes. I mean, all the processes that are happening in this disk can maybe also fit some models of planet formation. The unknowns are the presence of substructures within the disk. Also, we don't know if some disks are warped or not. Are they misaligned with the inner binary or not? This we don't know. What about magnetic fields? It seems that there's one target for which we see some magnetic fields. We see the jets, but they are not very collimated, so we need to constrain that. And also don't know if this disk actually forms second generation planets. However, we are now probing the whole disk structure from the inner regions with the VLTI, with the large program and some Matisse observations. I already talked to you about it. In the outer regions with sphere, in the visible and infrared, and there is a student, Katharina Hendricks, that is working on that with Devika Hans and myself, and we start to see very nice images of the surface of these disks, and you can really link the outer disk part with the images that we have of the inner disk parts of this target. So it is the same target, but at different scales with the VLTI on one side and the sphere on the other side. So we can really have the full constraint on the properties of these disks. And we also obtained some ALMA data in Ben7 and high angular resolution to resolve the dust, because I'm a bit late. So I will jump directly to the conclusions. So the main conclusions are that the disk around post-AGB binaries are similar to disk around young stars. And I hope that I managed to convince you. And they are similar enough, I think, to be interesting to study them to see if planet formation processes like dust grain growth, formation of substructures, and even planet formation itself is happening in this disk. It's very interesting to study them. We start to see signs of planet disk interactions in this objects. That is very exciting. That need to be further studied, I think. And I think that this disk can bring important constraints on the different planet formation processes, whether or not planet formation is actually happening in this disk, actually. And the last message is that we have a very large observing campaign to really constrain all the properties of this disk. So please stay tuned. I think there will be very nice results in the very, very soon. So with this, I will thank you very much, and I'm waiting for your questions.
Thank you, Jacques. Very interesting talk. Okay, I suspect that there will be questions. If you do have a question, please say so in the chat and I will call out your name. Anyone has any questions? Please, Karan.
Hi, Jack. Thank you for the nice talk and the great overview. And congratulations on the observing programs and the work. I had a question on the second generation planets that can form in these disks. Do you really think, in your opinion, that in these disks where there is modulation due to the interaction of the post-AGB star with the disk, it'll be stable enough for planets to form?
Yeah, so do you mean, do you think the interaction between the binary and the disk?
Yes.
Yeah. So we think that the binary will only perturb the inner disk regions, but the further away you are from the binary, of course, the disk will be less perturbed. And actually, in the simulations that we run, we see that the disk is stable for quite a long time. So I think what makes the disk dissipate is not the fact that the disk will not be stable or perturbed by the inner binary, but it's more star evolution, because the post-AGB will become very hot, and at some point it will start to photoevaporate the disk, for example. So I think this is the limiting factor. But the stability I think is not the problem, because we also have protoplanetary disks around young binaries that exist that are stable, and we know that there are planets that form around those young binaries. So.
Thanks. Joris, I have another question if I can ask.
Sure.
Yeah, so in a little bit earlier, you said that you could have a first generation planet that survives the AGB phase. Is this common? And if so, how does it actually happen?
Well, we don't know if it's common. If you believe that so if the interpretation that we have of the link between the transition disks and the depletion is actually due to the planet, it's more likely that this planet is first generation. And so it will be the first observational sign of it. How it happens, it's just that the planet must be relatively far away from the inner binary to survive. So the orbit of the planet will become larger after the AGB phase, where the evolved star will lose its mass, and so the orbit will just widen, but the planet will just stay around the binary. And then when the disk forms, it will just perturb the disk. So.
Okay, thank you.
Okay, now we have a question of Magdalena.
Yes. Hi, Jacques. Thanks a lot for your talk. It was really nice. I have a question. You already mentioned something answering Karan, but because I know that for young stellar objects and disks around them, you might have a different size of the basically of the cavity if you have a planet forming there that you measure from like polarimetric observations and millimeter observation. And I was wondering whether you would expect something similar for second generation planet as well, or if maybe your ALMA and sphere observation may allow you to say if like the planet formed as like a first generation planet or a second generation planet. So what I mean, if it's a first generation planet, if the effect of that planet on the disk would be the same as if the planet was formed in that disk as a second generation planet.
Yeah. So thanks for the question. I think it's one of the main questions, because actually I think it will be difficult to differentiate the effects from first generation planets from the effects of the second generation planets. Or if I put it in another way, I think it will be more easy. I mean, it will be possible to know, whereas if you have a first generation planet, for example, if your orbit of the planet is out of the disk plane, or if it's very massive compared to the mass of the disk, then you will know that it could not have formed within this disk, and it will be a sign of a first generation planet. But if you have a low mass planet within the disk, it will be very difficult to differentiate between first generation and second generation. So I think that is quite difficult to use planet-disk interaction to differentiate between the two kinds of planets. However, what we can do is try to study the planet population around white dwarf binaries. And this will be possible with the ELT so actually it's in my slide that I skipped, so thank you very much. I can come back to them. So with the ELT, you have the sensitivity and the angular resolution to really be able to be sensitive to the planets around white dwarf binaries. And we can try to build the population of these planets and see if there is an excess of planets that could have formed as a second generation in this disk. And also, interestingly enough, the gravitational wave can also help us to detect planets around white dwarfs. So the LISA mission is one of the goals also that they have, is that they will try to look for planets around binary white dwarfs. And actually, we are trying to work out what will be the effect of an excess of planets, so second generation planets, of the population of planets detected from the LISA space mission, for example. So I think it's more, we'll be able to make the link between the population of planets around white dwarf binaries and this and the physics of this disk. But in the disk, I think it will be difficult to know whether or not whether the planet is first or second generation. It can be even more complex than that, because you can have actually a rocky planet, first generation rocky planet that is massive enough, and then it will, at some point, it will be in a new second generation disk and will accrete more mass. It will go through a runaway gas accretion and it will transform itself on a giant planet. So you can have a second generation giant planet that was a first generation rocky planet, for example. So I think the answer will be more complex than that.
Okay, thank you. Does anyone else have a question? If not, then I'll leave everyone by thanking Jacques. Jacques, thank you very much. That was a very nice talk, and I'll hope to see everyone again next week, Friday afternoon. Bye.
See you.
Thanks, bye.